Hey guys, today we're taking a look at natural logarithms. Now remember, so far in this unit we've taken a look at common logarithms, which are log of base 10. Yesterday we took a look at logarithms with bases other than 10. And today we get natural logarithms, which are going to have a base of e. Now remember, we learned about this irrational number e. It represents the number 2.7182 ... So in other words, these natural logarithms are not going to be a rational number like 2 or 4 or 10. They're going to be this irrational number. And there's a reason why we call them natural logarithms, because they actually do arise in nature. So remember, logarithms are simply the exponent you raise a base to in order to get a power. So here we go. Let's jump into today's notes here. It says n is equal to the natural log of m. That natural log of m, if and only if m is equal to e to the nth power. So we've seen this terminology, log base 10 was equal to just simply log. Well, today, log base e is going to be equal to this shortened abbreviation of ln. This represents the natural log. In other words, what we're going to be doing is we're going to be finding the power we raise e to in order to get whatever that power is. So, for example, our first one says to simplify the natural log of e. What power do I raise e to in order to get e? Well, that's just the first power. Part B says take the natural log of e to the third. In other words, what power do I raise e to in order to get e to the third? Well, it's got to be the third power. And part C says what power do I raise e to in order to get 1? Well, remember, any base raised to the 0 power will give us 1. So the natural log of 1 must be equal to 0. Now, you do have the natural log button on your graphing calculator. So if you grab your graphing calculator and take a look at that, we'll show you what that looks like. These next few examples ask us to use our graphing calculator to round to the nearest thousandths. So let's take a look at the natural log of 325. So if we get our calculator going here we go, and we delete all that on there. You'll notice the natural log button is right down here on the left hand side. You'll see ln. So if we take the natural log of 325 and press enter, we see that we get 5.784. We'll round that to the nearest thousandths. The next one wanted us just to find the natural log of 8, so we'll take the natural log of 8 and press enter there. And again, these are the powers or the exponents that we're raising e to in order to get these numbers here. Now, just to show you some from the previous example here, if we took the natural log, and now right above the natural log you see e to the x, so if we hit second function e to the x and type in 3 and close our parentheses and press enter, we should get 3 back. So in other words, the power we raise e to in order to get e to the third is the third power. All right, let's keep moving down with our examples now and take a look at a few word problems. It says, ignoring the force of gravity, the maximum velocity v of a rocket is given by the formula v equals c times l, the natural log of r, where c is the velocity of the exhaust and r is the ratio of the mass of the rocket fuel to its mass without fuel. With a small payload, a solid propellant rocket could have a mass ratio of 19. A typical exhaust velocity of this rocket might be about 2.4 kilometers per second. Find the maximum velocity of the rocket. So this simply is a plug and chug type problem. Here, the maximum velocity is equal to c. C, remember, is the velocity of the exhaust, and r is the ratio of the mass of the rocket fuel. So you see that we have c is equal to about 2.4. So 2.4 times the natural log of r, which is about 19. So let's plug that into our calculators. V equals 2.4 times the natural log of 19. When you do that on your calculators, you should end up with about 7.0 meters per second will be our measurement for velocity. So that's simply just plugging in the correct numbers into the formula and using your natural log button on your calculator. All right, moving to example 3, it says the median height of girls aged 2 to 16 is approximated by this function h here. with the equation h of a equals 47.28 plus 40.86 times the natural log of a, where a is the median height in centimeters of a girl, a years old. So a is our age. Now it says to use the function to approximate the median height of a 14-year-old girl. So let's take h of 14, and this is equal to 47.28 plus 40.86 times 14. I'm sorry, times the natural log of 14. So caught me here. I'm speeding through this too quickly. This should be times the natural log of 14. All right, let's punch that back into our calculators. And when we do so, we get h of 14 should be equal to 155.11 centimeters. So bonus points if you can tell me how much that is in terms of inches, and if you fall above or below that medium height, because aren't you about 14 years old? All right, let's move on to the next example. Example 4 says, under certain geographic conditions, the wind velocity v at height h centimeters above the ground is given by this formula: velocity equals k times the natural log of h over initial h here, or h sub 0, where k is a positive constant that depends on air density, average wind velocity, and other factors. H sub O is the roughness value depending on the roughness of the vegetation on the ground. Okay, it says suppose that h of 0 is equal to 0.7 centimeters, the value that applies to a lawn 3 centimeters high. If the wind velocity is 435 centimeters per second, what is the value of k? So we're going to substitute our values in to this very complex equation to determine, I don't even know, but we have k times the natural log of the height of the grass, which we said was 3 centimeters, divided by its roughness, which was 0.7. All right, we're going to take the natural log of 3 divided by 0.7 and divide it over to the other side in order to get k by itself. So we'll divide both sides by 3, or side by the natural log of 3 divided by 0.7. All right, and that's going to leave k here by itself. And when we take 435 divided by the natural log of 3 divided by 0.7, we get a constant here of 298.9. All right, so we're going to use that constant here in this next problem. It says at what height above the ground is the wind velocity 1,500 centimeters per second? So we're going to substitute in here our 1,500 and set that equal to our equation using k as 200 and we're just going to round up to 299 times the natural log of h, the height that we're solving for, divided by our roughness of 0.7. Okay, let's start to get the natural log here by itself. We're going to take and divide 1,500 by 299 to get the 299 off. We're left with the natural log of h over 0.7 is equal to 1,500 divided by 299, which is approximately 5. Now remember, this line right here simply means e to the 5th power is equal to h divided by 0.7. Now e to the 5th power is simply a number in our calculators. We're going to just punch that in, and when we do so, we get e to the 5th is 148.4, I got to check my notes here, is equal to h over 0.7. Now to find the height of this grass, we need to multiply both of these sides by 0.7. And when we do so, we're going to get 103.9 centimeters. And that is a formula you will never need to know in life.